Hello everyone, welcome back to Introduction to Semiconductor Devices. This is lecture 2 of week 1. In the last lecture, we understood the basic properties of semiconductors. We said how the conductivity is different in various semiconductors. And then we said that to understand the reasons why the conductivity is in that way, we have to understand a little bit of quantum mechanics. And then we discussed about a free electron, how the dispersion is, in parabolic shape. And then if you confine an electron to a small dimension, for example, a potential well of dimension L, then you saw that the energies are no longer continuous, but they're discrete. For example, energies are E1, E2, and so on. So only these discrete states are allowed, and corresponding to each of those states, you have a wave function. A wave function is simply, it tells you the psi mod of psi square will give you the probability of finding an electron. So you see that for various energy levels or energy states, you have different probability distributions of finding an electron. And then we said that an infinite potential well, while it is a very simple problem to solve analytically, it may not be the accurate representation. So we wanted to understand how a finite potential well behaves. And then, while it is possible to solve a finite potential well analytically, we did not do that because it becomes a little bit more tedious than what is required in this course. So what we said was, okay, we did this, we solved this problem using a numerical approach. And then if you have a situation where the potential well has a depth V0, this is the depth of the potential. And we saw that there are these wave functions which look similar to the infinite case with some changes, of course. And the important thing was that the wave functions are now penetrating into the barrier regions, especially the higher energy wave functions. For example, this is a 6 wave function, and that has significant amount of penetration into the barrier region. And this is not expected in the classical terms. The reason is, if you take let's say a cricket ball and throw it at a wall, would you expect the ball to go to the other side of the wall? You would not, right? Because the energy of the ball is very small, the barrier is very strong. But if you do it with a great force, then it might actually break the wall, but that's an extreme situation. A similar situation happens even in the microscopic scale. And I'll just briefly mention a problem which is very similar to a potential well, which is basically a problem of a potential barrier. So you could think of a potential barrier where you have a barrier of height V0 in the region 0 to L, and then everywhere else the potential is basically 0. Okay? If a particle is incident on this, what happens? Okay, so if your particle has an energy E, and if the energy is greater than V0, it just simply goes no problem. But if the energy is less than V0, classical mechanics tells us that there is no probability of finding the electron on the other side or particle on the other side. This is if you look at transmission here, transmission probability. What is it? For example, if I have 100 particles incident on the barrier from the left side, how many of them will actually get transmitted to the other side? That is the transmission probability, right? So classical mechanics tells us that you don't have any probability of finding the other side, particles on the other side. But then quantum mechanically, there is a finite transmission probability, and you could actually solve it and get an expression. There is some function of E and then V0 and then the size L and so on. You could get a function, but it's not important for us at this moment. But later on, we will actually come back to it when we discuss MOSFETs and discuss how current flows through the gate oxide of a MOSFET. This finite transmission probability becomes important, and we will actually discuss it in a greater depth there. But in any case, I would actually give you a problem in the homework 1, wherein I'll try to ask you to compute a few transmission probabilities for this barrier case as well. It's not difficult. You have an equation and you will be able to do it very simply. You just try that in the homework. All right. So now let's get back to what we were discussing. This potential well, the 1D potential well, looks like a toy problem, right? It's quite simple to solve. How does it help us, right? That's a question that must be in your minds right now. But I would argue that this is a simple problem, but it actually captures quite a lot of essential features of what happens in atoms. If you think about an atom is simply consisting of a nucleus and electrons which are orbiting the nucleus. So there is a Coulombic attraction between the electrons and the nucleus, right? So if you have a charge Q, how much is the potential around the charge? you could calculate it. You would have done it in electrostatics. It is simply the potential is going to be proportional to Q by R, right? So all around the nucleus, you have a potential of the form 1 over R. Okay. And what is this potential doing? It is essentially causing the electron to be confined near the nucleus. So what is the dimension of an atom? It would be maybe, let's take it to be 1 or 2 angstroms, okay, 1, 2 angstroms. The lattice constants are usually 3 to 4 or 5 angstroms. So the size of the atom is going to be smaller than that. So this potential, 1 over R potential, which is surrounding the nucleus, is causing your electrons to be confined in this region, right? So what happens in that scenario? Well, in the 1D case, we saw that there is this discretization happening. In a 3D case also, something similar happens, okay? Because now the potential is different. The potential well is actually a three-dimensional potential well. So you have, all the R directions. In the radial directions, you have this potential well, which causes the energy to be discretized. And you have these quantum numbers, n equal to 1, 2, 3, and so on, right? Similar thing happens. And you have energy levels, E1, E2, E3, and so on, which are actually occurring within the potential well. This can actually be calculated analytically, but it becomes a little bit tedious, and we don't want to do that for this. For the purposes of this course, it is enough if you understand that this sort of a quantization happens. Well, it's not that simple because we have one more step. We have a three-dimensional potential when compared to one dimension, so we have additional quantum numbers. N is one quantum number, which we have already seen. Now the other quantum numbers we have to introduce, which are called as L and M. Okay. These are additional quantum numbers that come in because of the symmetry in the azimuthal direction and in the polar direction. And there is going to be some variations of probabilities. Well, actually, I'm sure all of you have seen this in a different form already. Okay. When you studied electronic configurations in your +2, you would have seen that there are this s orbital, p orbital, and d orbitals. Well, those are essentially probability distributions in space. And that can be exactly calculated by the technique I just described. I mean, if you go through the math, you would actually get these shapes. In the 1D case, you saw that the probability was varying as a function of x. In a 3D case, the probability will vary as a function of x, y, and z. Okay, so we have this quantum number n, which is actually capturing the confinement in the radial direction, because of which you have 1, 2, 3, and so on states. And the quantum number L can have 0, 1, 2, and so on. When L equal to 0, essentially, you would have understood this as s orbital, which means that your probability is uniform in a spherical, in all directions, the probability of finding a particle is uniform. Okay. Whereas if you put L equal to 1 and solve that, you will see that the probability has this dumbbell shape, which you would have studied as p orbital. Okay. And what is more, whenever you have L equal to 1, M can take three values. It can go from minus L to plus L. So in this case, it will go as -1, 0, and 1. And these are the three levels which quantum numbers which are allowed, which result in three energy levels at the same energy. I mean, there are three levels at the same energy, which we call as degeneracy. So you have this, Px, Py, and Pz. These are essentially energy levels that, they have the same energy, but then there are three distinct levels, and we call them as degenerate levels. Similarly, if you go to L equal to 2, you have a d orbital, which is again having m from -2 to +2. So there are 5 degenerate levels in the case of d orbital. And because of that, you have these energy levels which you get. For example, S you have 1s, 2s, 3s, and so on. And in P you have 2p, 3p, and so on. And in D you have 3d, 4d, and so on. And the corresponding energy levels are drawn to scale in this picture. And so, in your chemistry class, or in the +2 level, they would have told you to actually say that, okay, remember the electronic configuration, right? 1s, 2s, 2p, 3s, 3p, 4s, and so on, right? You just remember the sequence. The reason that sequence comes about is because of the energy, the way the energies are distributed. Okay, and we already know from Pauli's exclusion principle that each of these energy level cannot be occupied by more than 2 electrons. At most, you can have 2 electrons, right? You can have no electrons, or 1 electron, or 2 electrons at most, right? So how does this help us? Well, if you think of silicon, right? Take an example of silicon. Silicon has an atomic number of 14. That means it has 14 electrons, right? How are these electrons distributed? Well, we start filling the states from the bottom, right? Because the bottommost levels are, have the highest probability of it being filled. So you can assign 2 electrons in the 1s state, 2 electrons in the second 2s state, and then there are 3 of these 2p states. There are threefold degeneracy. So you can assign 2 electrons to each of these, and then so we have filled up 10 electrons, and you have 4 more. So you will fill 2 in the 3s state and then 2 in the 3p state. So this is how electrons are distributed, and this has very profound implications on how the energy bands form. That's why I just wanted to review this. So now what you see is, you could also think about it in the Bohr's picture, right? In a Bohr model kind of a representation, you could think about it. So this is how it looks like. This is the previous case was an energy level representation. This is a physical representation. So what you see is that in a silicon atom, you have the nucleus, which has these, protons, which are, in the nucleus, so plus 14 charge, and you have first shell consisting of 1s, right? First shell means n equal to 1, so 1s. It has 2 electrons, okay? And the second shell is consisting of 2s and 2p, which has again in total 8 electrons, because 2s is 2 and then 2p has in total 6 electrons, so 8 electrons in this, okay? And then you have the third shell, which is n equal to 2, where you have s and p orbitals, okay? The s orbitals are filled up, 2 of them, but the p orbitals have 6 allowed states. This is important, right? This makes a big difference. So they have 6 allowed levels in the p orbital, right? Because we have 3px, 3py, 3pz, right? And out of which there are only 2 of them which are filled up. So what is the total number of available states in the outermost shell? It is basically having 3s and 3p. So this has 2 plus 6, total 8 available states, okay? 8 states are available, out of which 4 are filled, okay? So this is very, very important. And we actually give this, a special name. We call the outermost shell as a valence shell, to just emphasize that, the spelling is, I think, is wrong here. But anyway, valence shell, which is basically having 8 states and 4 are filled. So it's exactly half filled. And the inner shells, the n equal to 1 and n equal to 2 shells, are really very close to the nucleus, and they do not play much role. So they're not really that important. So we call this as a core, okay? This entire thing inside, we call this as a core. This does not really play much role in the electronic properties, but the outermost shell plays a huge amount of, creates a huge amount of difference, all right? So, but this is still a single atom, right? And you are almost never going to look at atoms individually. You're going to look at collections of atoms. So how do we understand collections of atoms? To do that, we have to understand a little bit more.